So, Monica, Elias, Monica. So tell me, how many electrons are we talking about? Just to start with, all together, how many electrons? 8 electrons to start, excellent. And then inner shell, 2, leaving how many in the outer shell? 6, exactly. All right, thank you, Monica. So we've got our inner shell. This is totally not to scale, but our inner shell is going to have 2 electrons. And our outer shell, you got north, south, east, and west. We got to get 6 out there, all right? So let me call somebody else. How is that structured? So Nathan or Nathaniel, Burns, Harold, Nathaniel, tell me, how is it structured? How are they structured? How many pairs? How many singles? 2 pairs and 2 singles. That gets you 6. That's exactly right. Thank you, Nathaniel. So you would get, and it doesn't really matter how you draw them. There are 2 singles and 2 pairs, right? And actually, let me draw it slightly differently. I'm sorry. Let me make my pairs here and my singletons there. It doesn't, from this point of view, it doesn't matter, but it makes it easier for me to draw in a second. So, my next question is going to be, how many covalent bonds? Let's see. I should have thought about this one. So Jessica, Edward. Jessica, are you here? Jess, tell me, how many covalent bonds does it want to make? I got 2. That's exactly right, okay? Because it just needs 2 more, just needs to share 2 more, and it will be a happy atom. So it needs 2 electrons for a full outer shell. Therefore, we'll make 2 covalent bonds. Cool. So you could write the structure of oxygen like this. Okay. And covalent bonds go here. Here. And these things have a really, let me draw this carefully. These guys, this one and that one, are called lone pairs. And there are some really unfortunate bits of terminology in science, and this is one of them, right? We just have to live with it. That's what people call them, right? The thing is, how can something be a lone and a pair? That makes no sense whatsoever. Right, we have to live with it, right? So the deal is, those are those pairs of electrons. It turns out, even though they're rather unfortunately named, they turn out to be extremely important in something called hydrogen bonds, which we will worry about in a big way soon. It's another one of those promises I have to deliver on. Trust me, they're important, okay? But they have this really unfortunate bit of naming. All right, so let's do kernel charge. What do we got? Nutan, are you here, Nutan? Tell me, sir. All right, there you go. Kernel charge. Well, so what's the charge on the nucleus to start? Or what you want to do? Pardon? It's 8 minus 2. That's exactly right. Thank you. So the charge on the so the kernel charge is 8 protons. That's a terrible 8. 8 protons minus 2 inner shell electrons is plus 6. So, more or less the same electronegativity than carbon. More. Because the blob in the middle's got a plus 6 charge, so those guys in the back row are feeling plus 6 pulling on them rather than just simply plus 4. So it's going to hold on to them more tightly. So therefore, it's more electronegative, or I should put it this way, higher electronegativity. God, my handwriting is terrible today. Than carbon. Okay. All right. Question. All right. What I wanted, yeah. Yeah, so exactly. The question was the covalent bonds of the empty spaces. Covalent bonds are to satisfy those empty spaces, right, to make the atoms happy. That's exactly right. That's where the covalent bonds will happen. All right. So rather than doing all the atoms we care about, I want to make a summary. All right? And atom number of covalent bonds and electronegativity, roughly. All right? So if we do hydrogen, it makes one covalent bond, and it turns out to have medium. Chemists would make a fuss about being this vague, but for our purposes, that's what we need. Carbon makes 4 covalent bonds, and it also has medium. Nitrogen, I want to leave that alone for a second. This is the clicker question. All right, I'll come back and fill it in for the notes. It turns out to have high electronegativity. Oxygen, we already saw. It makes 2, and it turns out to have high electronegativity as well. And then there's 2 sort of strange things. So sulfur, well, sulfur actually looks the same as oxygen. They're in the same row of the periodic table. It makes 2, and it has a medium electronegativity. And phosphorus is in the same group as sulfur. It turns out to make 5 covalent bonds, and the reason for that I'll explain in just a second, and it's medium. These 2, it turns out that both phosphorus have outer shell electrons in the 3rd shell. So it turns out if you go and if you look, phosphorus and sulfur have outer shell electrons in yet another shell, which has a greater capacity, and so they behave slightly differently. Sometimes you will actually see sulfur making 6 bonds on very rare occasions. All right, so there's some odd things when you get into the higher shells. We could explain them. In fact, the chemists do it all the time. I just wanted to give you a thumbnail sketch of how this basically works. It's these same principles applied at a larger scale. Questions about these? All right. What I'd like to do is give you time to think through nitrogen, and I'll mark it up there in a second. That the clicker question is, so what's the appropriate structure for nitrogen? And from that, you can conclude all these various properties. I'll fill it, like I said, I'll fill that in a second. So let me erase this, and I'll get the clicker started. Let's see, we'll get rid of that.